back, guys, for the next video. Today we are going to be focusing on video 6-2, so we'll be talking about colorimetry and enthalpy calculations. So I know we did a little bit of this in lab already, and we focused a lot about endothermic and exothermic reactions and how that has to do with enthalpy. But what we're really going to focus on now is actually performing the mathematical calculations that are associated with those particular concepts. So it's going to be a really exciting day. Again, just a reminder, I'm Jayland Bio. Make sure you like, subscribe, leave a comment down below. I've got a merch store as well. Got some hot merchandise going on, so feel free to browse around and see if you see something you like. Let's move on. So our learning objectives are actually pretty straightforward today. We should be able to explain concepts related to calorimetry, and then also calculate energy and entropy using a variety of different strategies. So calorimetry is the measure of heat flow, and this is usually done using a device known as a calorimeter. Now, a lot of times what you'll see in lab is that we will use styrofoam cups as a way to help measure heat flow. The reason for this is that they are good insulators and they don't allow a lot of transfer of heat to the surroundings. Remember, we want to try to mitigate as much interference in a thermodynamic process as possible. So by providing good insulation, we can prevent the air around the styrofoam cups to either absorb heat or to provide heat for the reaction that's taking place. Now, obviously, the more heat an object gains, the hotter it gets because the kinetic energy of the molecules increase and therefore the temperature gets warmer. The magnitude of the temperature change varies from substance to substance in presence of the same heat change. So we can provide the same amount of heat for two different substances, and one substance will get hotter than the other. Now, that characteristic is known as heat capacity, and that is the amount of heat that is required to raise the temperature 1 degree Celsius. Again, this is different for different substances. Some substances absorb heat very readily, and therefore the temperature increases quite quickly. Other substances require more energy to create a change in temperature, and a lot of that will have to do with the type of forces that are present between the molecules. But we'll talk more about that later. Now, there are two different types of heat capacity that we are going to focus on here. We have what's called molar heat capacity, and essentially that's the specific heat for a mole of the substance. We've talked a little bit about specific heat before, and that is represented by the letter C, and that's focused on 1 gram. So remember, if you remember seeing 4.18 for water, that is the specific heat. The molar heat capacity is going to be something quite a bit different. So as we talked about before, this means that different substances require more heat to increase 1 degree Celsius. Now, water has an unusually high specific heat when we compare that to other substances. And when we look at energy transfer, because all of this is directly related to energy transfer, it happens really one of 3 ways. Either physical through heating or cooling, another physical change, which would be something like a phase change, so freezing, vaporization, etc., or a chemical change where we are breaking chemical bonds and making chemical bonds. As you see below, you have the specific heats of some common materials, including liquid water, solid water, water vapor. All of those, interestingly enough, are significantly higher than any of the others that are listed here. So keep in mind that water does have a very high specific heat capacity. Now, the amount of energy, Q, can be calculated with the given formula. Q equals mc delta T, where Q is energy, and that is measured in joules, M is mass, and C is the specific heat. Delta T is the change in temperature, or the final minus initial temperature. Molar heat capacity can be found using the specific heat and converting that using the molar mass to the molar heat capacity. Rather than using grams in the calculation, we would use moles as well. So just a couple things that are different there, but keep in mind you have specific heat capacity, which is used in grams, so M is going to represent by mass. You could also use molar heat capacity as well, in which you would have the moles of the substance. Either way, you're going to get roughly the same answer. So let's take a look at a practice problem to help us out. And notice it very specifically says the word heat in here. If we're looking for enthalpy, it will ask for enthalpy. Okay, so there is a difference there. How much heat is needed to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius if the specific heat is 4.18 joules over grams times K? Now, one thing to keep in mind here, notice that there is the specific heat is in K. Sorry, it's in K. And your temperature is in Celsius. Now that is okay because if you remember, the difference of these two numbers, these two temperatures in Celsius is going to be the same as their difference in Kelvin, right? Because they are both absolute scale. The Kelvin is the absolute scale of Celsius. So as a result, you do not need to convert those values to Kelvin. So if we just use the formula we just previously talked about, Q equals mc delta T, we could plug in numbers and solve. So the question is asking for Q. We have our mass. We have our specific heat, which is 4.18. We have our change in temperature, final minus initial, so we're going to take 98, and we are going to subtract 22. And now you would just plug into your calculator and simply solve for Q. So when we plug in our numbers, we get the value for Q, which is 79,420 joules. It may ask you for that in kilojoules. If you would, if it does ask you for that in kilojoules, you would simply divide by 1,000. So we get or 79.42 kilojoules. The next question actually asks you, what is the molar heat capacity of water? Well, we know the specific heat capacity. The specific heat capacity is 4.18, and that is joules over grams per degree Kelvin, or per unit of Kelvin. So we need to be able to get this into moles. Well, in order to do that, we just simply use the molar mass. All right. Now in this instance, we need grams to cancel, so grams is actually going to go on top. We're looking at water. The molar mass of water is 18.02. That's grams per every 1 mole. So our grams are going to cancel. We simply just do a little bit of math here. So we're going to take 4.18 times 18.02. And what we get, including our units, is 75.3 joules per mole Kelvin. All right. So again, just make sure you read each question carefully, especially when we start going in and focusing on enthalpy calculations versus heat calculations. One other thing to keep in mind in terms of energy when it's added to a system is the energy that is used to make a phase change occur. As energy is added to a system, the temperature typically increases because there's more kinetic energy in the system, and therefore the temperature, as a direct measurement of kinetic energy, would increase. However, this is not the case during a phase change. A phase change simply requires energy to happen. So going from 0 degrees Celsius of ice to 0 degrees Celsius of water does require 6.01 kilojoules per mole to be added to the system. Now the opposite requires 6.01 kilojoules to be removed from the system. Remember that this is added to the system because this process is endothermic, right? It takes energy to break those bonds. We look at the opposite process of freezing. That requires 6.01 kilojoules to be removed from the system, and therefore is an exothermic process. Okay, so keep in mind that phase changes do require energy to happen. Even though the temperature does not increase, energy is added or removed from the system. So there are really 3 ways that we are going to work on calculating enthalpy of reactions. The first one is utilizing Hess's law. The second one will be utilizing enthalpies of formation, and the last one will be using bond enthalpies. The enthalpy value for a reaction can be easily calculated using known values. Hess's law states that the total enthalpy change is the sum of the individual enthalpies that are found in the reaction. So if we take a look at the reaction here, the combustion of methane yields negative 802 kilojoules per mole. Also, we have to keep in mind that the gas is transformed into a liquid, so we need to include that in the calculation as well. So 2 H2Os of gas to 2 H2Os of liquid is negative 88 kilojoules per mole. It's very similar to what we did in the previous unit, where if we have something on the reactant side and something on the product side, we can actually cancel those out, thus leaving us with the correct formula for the combustion of methane and a total change in enthalpy of negative 890 kilojoules. This does tell you that the reaction is quite exothermic, as the change in entropy is very negative. All right. So a couple rules to consider as we go through and do this. If you flip the reaction around, so for example, you may have to take the reactants and products and flip them in order to get everything to cancel appropriately. If that is the case, then the sign on your change in enthalpy is reversed. This becomes really important when trying to figure out how each individual reaction can work and cancel to make your overall reaction. You'll see this in practice. You also may need to multiply your delta H by whatever coefficients are in your full equation if they do not match your individual enthalpy changes. So the equation you may get for enthalpy may not match the stoichiometric ratio that you find in your problem. If that is the case, you need to multiply your delta H and all of your species by that particular number. This really is better explained in practice, so hopefully you'll see it with the few practice problems that we do. So the enthalpy of reaction for the combustion of C to CO2 is negative 393.5 kilojoules per mole. And the enthalpy of combustion from CO to CO2 is negative 283 kilojoules per mole of CO. So using these data, calculate the enthalpy of combustion from C to CO. So our job here is to go through and figure out how can we get this equation here utilizing these two equations, utilizing some of the tools that we've talked about before. Well, I noticed that C is on the left-hand side, so we're probably going to want to start with that first equation just as is. So we have carbon plus oxygen. I'm leaving out the states of matter for now. To CO2. And the enthalpy for that is negative 393.5 kilojoules. All right. Now, if I take a look, I need to get carbon dioxide by itself on the product side, but in the second equation, it's on the reactant side. So what I'm going to actually do here is I'm going to reverse that entire second equation. If I reverse that entire second equation, then CO2 is going to cancel. I'm actually going to get half of an oxygen to cancel, and that leaves carbon monoxide as our product. You'll see what I mean here in just a second. So I'm going to reverse that entire second equation. So we're going to take CO2, and that's going to yield 1/2 O2 plus CO. Now remember, when you reverse that, then the enthalpy sign changes. It gets reversed as well. So this ends up being actually a positive 283 kilojoules. Well, my COs cancel. I get half of an oxygen that cancels. And what's left is my full equation. Okay. So now all I need to do is do some simple math. Negative 393.5 kilojoules plus 283 kilojoules. I'm going to get negative 110.5 kilojoules per mole. Okay? That's all there is to it. You just have to look and see how you can rearrange those equations to get what you need to cancel. And then once you get all those things canceled, rearrange your signs, or if you have to do some multiplication of your coefficients, take care of that. And then just simply add, and that calculates the enthalpy of the reaction. Pretty straightforward. Let's do one more problem. So for this problem, we're going to follow the exact same steps here. We need to get this equation here, and we're going to use these respective enthalpy changes down below. Now, if I look at the first part here, I need 2 carbons in my reactant side. Well, I'm only given the enthalpy of carbon plus O2 to yield CO2. So in this instance, what I'm going to do is I'm going to actually take that and I'm going to multiply that by 2. So we're going to get 2C plus 2O2 yields 2CO2. And as a result of that, I'm actually going to multiply the enthalpy here times 2 because I multiplied all of my chemicals times 2. So in order to do that, we're going to multiply that number by 2, and we're going to get negative 787 kilojoules. The next thing I notice is I need to get C2H2 on the reactant side. So I'm going to take this sucker up here and I'm going to flip it. Okay? So we're going to get 2 CO2 plus H2O yielding 5 halves. Kind of weird to think of that. Plus C2H2. Okay. And again, we flipped that. So that's going to be a positive 1,299.6 kilojoules. Okay. And we take a look at the last equation. Well, I need to get H2 in my reactant side, so let's leave that as is. So we got H2 plus 3 halves of O2 yields H2O. Okay, we left it as is, so that's going to be negative 285.8 kilojoules. So let's see if we get stuff to cancel. That's going to cancel. That's going to cancel. 3 halves. So 1 half. Oops. That's okay though. I was wondering why it didn't cancel out. So these actually all cancel as well. So what we end up with is 2 carbon plus H2 yields C2, H2. Nice. And then you add them all up, all your bond enthalpies, all your reaction enthalpies, and you get 226.8 kilojoules per mole. All right. Again, same concept as what we talked about before. You just need to make sure that you go through and calculate those to the best of your ability, all right? Make sure you understand that you can multiply them and you can flip them. You just need to make sure to remember to multiply, run that through all of your coefficients and make sure that you multiply your delta H's by that or flip the sign if necessary. Let's move on. So the standard enthalpy of formation is the second way that we are going to be able to calculate delta H for the reaction. The enthalpy of formation, like I said, is another way to do that. We look at the formation of the compound of individual atoms, and these are usually given in a table. The enthalpy of formation for the entire reaction is given below. The reaction is the sum of the enthalpy of formation of the products minus the enthalpy of formation of the reactants. Keep in mind that these are values per mole, so you'll need to multiply the coefficient for each species. So when you look at these types of problems, you're not going to be given formulas, but rather you're just going to be given compounds or molecules. You'll be given the enthalpy of formation for each of them. You'll need to take the sum of the products and subtract that from the reactants to be able to solve. Let's do a practice problem. So here we are given a equation and we are given a table with our enthalpies of formation. So with this, we need to calculate the standard enthalpy change for the reaction. Now remember, the enthalpy change is the sum of H of your products minus the enthalpy change for your reactants. All right? So your products, what we have is we have 6 waters. So 6 minus times 241.8 plus 4 NOs. Notice how the coefficients come into play here. And we're going to subtract that from the reactants. That's it. That's all you have to do, guys. Any element by itself actually does not have a standard heat of formation, so you don't actually have to worry about that, okay? And so you do the math here, get your calculation, and you end up with 905.2 kilojoules per mole. Okay? So again, pretty straightforward there. And again, you know delta H there. You know delta H is positive. And since delta H is positive, that indicates a strong endothermic reaction. All right, let's move on to the last set of problems. One final way we can calculate enthalpy is by using the enthalpy of each bond in a chemical species. Reactants break apart. Keep in mind, so they take in energy. Remember, that's an endothermic process, and products are formed, so they release energy, so that is exothermic. If the energy released is greater than energy formed, it's exothermic, and vice versa. So basically what we're looking at is we're looking at the enthalpy of the individual bonds of the chemical rather than the total heat, enthalpy of formation. We're going to add up the bonds that are broken and subtract the bonds that are formed, and then we will be able to get our enthalpy for that reaction. All right, so if we take a look at this, we're given an equation. It doesn't really tell us a whole lot, but with this, we want to calculate the enthalpy of the entire reaction that's going on here. So what we need to do is we need to count bonds and multiply by them. We're going to take the bonds that are broken in the first part, and then we're going to take the bonds that are formed in the second part. We're going to subtract those two numbers to determine the total enthalpy of the entire equation here. So if I take a look here, I have one carbon-carbon bond, okay, and that is 347 kilojoules, okay, and then I have 1, 2, 3, 4, 5, I have 6 HH bonds, and those, I'm sorry, six carbon-hydrogen bonds, and those are 413 kilojoules. So remember, we're going to multiply that number by 6. Okay? And then I have 1 chlorine, and that is 239. All right? Add all those up, we get 3,064 kilojoules. Now we're going to subtract what was formed. In this case, I still have 1 carbon-carbon bond. I now have 5 carbon-hydrogen bonds. So it's 5 times 413. I have 1 carbon-chlorine bond. 339. And I also have 1 hydrogen-chlorine bond. And that is 427. I'm going to take the sum of all of those values, and what I get is 3,178 kilojoules per mole. Subtract the two answers, and what you get is an answer of negative 114 kilojoules per mole. There we go. All right, pretty straightforward there. So make sure you add up the number of bonds, make sure you count them up, and also make sure that you multiply the enthalpy of the bond by how many bonds there are, and then just subtract the two and you get your answer. Okay? Pretty straightforward. Hey, I'm going to end the video here because this is a relatively long video, and I want it to be done and over with. So I hope you guys have a great day. This is J-Land Bio. Make sure you like, subscribe, and make sure you shop the merch store. Right? We'll talk to you later, guys. Have a great day. Bye-bye.